Thanks, Nara, for the introduction. And thank you all for staying to the last talk of the Scala Symposium 2017. I'm really happy to talk today about algebraic effects and our library implementation, which is called Scala Effekt. And it actually runs in Scala, in Dotty. I'm not sure about Scala with K. I don't know whether you read John Pretty's announcement there. And in particular, I want to talk about a couple of design decisions that I think are interesting and share our insights with you on these decisions. So I assume that each of you has at least once implemented something and used side effects, right? And maybe you felt a little bit like that at some point. And for this talk, I'm going to take a wide notion of effects. So there are very low-level effects like networking, state, exceptions. But then I also like to think of configuration or context-dependent information as effects. HTTP requests are a bit on a higher level than networking, but they might use also other effects for implementation, right? And then on the high end, we have something like APIs, which I also like to think about as effects. And in addition, for this talk, I want to assume that we also want to handle them locally. So much like you handle exceptions locally, we want to handle them in terms of other effects, much like you want to rethrow exceptions when you catch them. And we also want to handle them differently in different contexts. So for instance, if you want to test your software system, you might want to use some other handlers for your network or for API stubbing or something like that. But last but not least, we also want to reason about them. And this is where the bears come in again. Because it's hard to reason about a system where you have, where it appears like there's non-determinism in some way. Okay. So this talk is about algebraic effects. And in particular, I think of algebraic effects as a very powerful way to structure your effectful program. So we have just seen the notion of effects I'm talking about right now. And algebraic effects work on every single level of these different levels, like from low-level effects up to API level. And in particular, algebraic effects allow you to split your effectful programs into 3 parts. So first we have effect signatures, which are like a collection of effectful operations. And they act as an interface. And they act as an interface between your effectful program, where you use your effect operations. But the semantics, the exact semantics of your effect operations is left open. You yet don't know what it means to trigger this effect. And on the other side, there are effect handlers, and those specify the semantics of the effect operations, right? So with this very high-level explanation of algebraic effects, let's dive into a concrete example written in Scala using the Effekt library. So this is a standard example in literature. It's a drunk trying to flip a coin. In particular, we see that there are 2 effects in use. So we have a flip effect, and we do have a raise effect here. So these are the effect operations, okay? So let's read through this example. So first we try to flip the coin once to determine whether we caught the coin actually or not. And if we now caught the coin, we try to flip again to determine whether it's heads or tails. And if we dropped it, then yes, we raise an exception. So this is an example of using two effects in one program. And this is also reflected on the type. So in our type, we see it eventually will return a string, but it uses 2 different effects. It uses the ambiguity effect, amp, and an exception effect, xc. Okay? As I said earlier, these effect operations, they just mark like positions in the program which are effectful, and our effect signatures tell us, okay, there are still unhandled effects. And we could not just run this program because there are unhandled effects. So in order to run our program now, we need to wrap this program into effect handlers. So one effect handler here we see is XC option, which interprets exceptions into the option type. And we see another one, which is amp list. It interprets ambiguity into the list type by enumerating all possible control paths. And in particular, we first handle the exception effect, then the outermost handler is the amp list handler, then we handle the amp effect. And so these are the effect handlers. And this will result into this, in this result here when we actually run the program now, because all effects are handled. And in particular, notice that we have this none as a third element of this list, which corresponds to the failure path when we encounter the raise effect. Yes, the raise operation. Algebraic effects are very powerful in the sense that we can also just now swap the two handlers without any further wiring or boilerplate here. And this changes semantics, okay? So if we now run the program, we get none. Why is that? We have one exceptional case, and it will jump over the amp list handler here to the XC option handler, and then this one just gives up and says, okay, just return none. No need to evaluate all the other paths. With that basic intuition now, let's look at how the effect signatures amp and XC are actually defined. In Scala Effect, in order to define signatures, effect signatures, we need to inherit from some marker trait called F. And the only important thing that this marker trait offers is actually this type member here, op, and this stands for effect operation. Okay. So now if you want to define amp and XC, we inherit from F and define these two effect operations. For flip, it's this method flip here, and it returns op Boolean, so it's a Boolean operation. We don't know yet what op is, but we see that on the next slide. And XC just defines raise, which works for all A's. So it's essentially like nothing. We could also use op nothing as a result type here. And if we now want to implement handlers for this effect signatures, then we inherit from another library trait, which is called handler. And one thing that's important here is that handler actually takes two type parameters, R and res. And R is the type of the program that the program usually would return. So in our introductory example, that would be string. Okay? And res is the type that the handler interprets our program into. This becomes more clear when we now look at the amp list handler down here. So it works for all R, but it interprets R into list R. Okay? So in order to implement it, we need to provide two things here. One is an implementation for this method unit. So up here we see it's R to res. Unit essentially is if you don't use any effect in your program, for pure values, the unit tells you how to go from R to res. Okay. In our amp list handler, we just wrap this value into list A in a single list. There's no ambiguity in our program. We just return this one single result. And we also need to implement all the effect operations in our signature. And here we only have one, which is flip. And how do we do that? And one key component of how do we do that is what's actually op. Okay, and we see that up here. It is something which very much looks like a CPS transformed version of A. So it's A to res, but then there's this control thing, which we won't look into detail today. It's only important that it's a monad, and we can use for comprehensions. So in our amplest implementation down here, we see, okay, this first argument, resume, it's actually of type string, okay, for this case it's R, no, it's Boolean, Boolean to control rest to control rest, so it's the continuation actually, and we call this continuation or this context of the effect operation twice. We call it once with true, once with false. We get lists because we interpret into a list, and then we concatenate the list to enumerate all of the possible control flow paths. Okay, so now we have seen a basic usage of effect. We have seen how to define effect signatures. We have seen how to define effect handlers. And now I want to talk a bit about the design decisions that we were faced with when implementing a Scala effect. And in particular, I want to talk about three different questions that we encountered. The first one is, how do we actually capture the context of effect operations? So the context corresponds to this resume continuation that we have seen in the handler implementation. And our answer to that question is we use a monadic implementation of multi-prompt delimited continuations, which I won't go into detail, but I'm happy to talk to you offline about that. And I also can point you to this paper, which is a really great paper, I think. It's a monadic framework for delimited continuations. And basically, the implementation of Effekt is highly inspired by this paper, that part of Effekt. Okay, so the second question we are faced with is, how should effect handlers provide semantics to effect operations? We have already seen how to use them, but how do they actually provide semantics? And different implementations of algebraic effects choose different answers here. And our answer is we use a shallow embedding of effect handlers, and I will go into detail in a second here. And the third question is how to establish an effect typing discipline. How do we manage to ensure that in the end, when we run the program, all effects are handled? Okay. And our answer is we use something that we call capability passing style. We pass down capabilities. Okay. It's interesting, I think, to note that for all of this, for each of these three answers, implicit function types, which have recently been introduced to Dotty, are a perfect fit for implementation. We'll see that in a second again. So let's now first talk a bit about shallow embedding of effect handlers and what I actually mean by that. So if we now again think about what it means to call an effect operation, we can think of effect operations as constructors of some effectful language, right? So here's an abstract schematic way of thinking about it. We have two effect operations, op1 and op2, and they also take some arguments here. And in addition, they also take a continuation. This is the rest of the program. Okay. If we now squint a tiny bit, we see that it looks really regular, this tree of effect operations. And in fact, if you maybe know some effect libraries which are based on the free monads, this is actually the regularity that those libraries abstract over. So if we look at a very simplified variant of a free monad here, we see that the continuation part is now abstracted out into this constructor impure, so such that the operations now are only like commands that we send around. And this tree structure is factored out into the free monad. Now to handle effects, those libraries, they write recursive interpreters, recursing over this tree and encountering operations and then providing semantics to these operations, okay? And in PL terms, we can think of this as a deep embedding of effect operations because we build up this tree of operations, then we have a recursive interpreter over this tree and provide semantics. And in particular, some libraries have the design decision that they say, okay, for one handler, one handler should handle all of the operations equally, so it should be the handler for the dynamic scope. And this design decision is also often referred to as deep handlers. And in particular, it's important to note that if you follow this approach, you can implement this recursive interpreter as a fold, as a simple fold. And when I think fold, I think many different things that are related to that. In particular, I think shallow embedding and polymorphic embedding, finally tagless, church encodings, internal visitors, object algebras. Maybe you know some of these, and they are all different concepts, but they have one common key idea, and that's don't build up the tree to then fold over it again, but immediately call into the semantics. Immediately call in, yes. provide the semantics just in time. And this is the concept that Scala Effect is built on. So if we now look at the schematic overview of how it would look in Scala Effect, we immediately call into the handler. So instead of building up that tree, we call the operation on the handler. What seems a bit like a small difference actually makes a big difference, and I want to share some technical insights with you. One is that typing becomes much easier. We don't have to deal with GADTs. So if you ever implemented something with Fourier monads, you might know that there are GADTs involved. We've seen this type parameter x before. That's existential, and it gets quite involved if you want to do that in Scala, or even worse if you want to do that in Java. Okay. B, we replace pattern matching on this effect tree by dynamic dispatch. And this benefits performance on the JVM because we don't need to do this pattern match at runtime, but we just jump to the method implementation. And also we don't need to find the corresponding handler for one operation because we immediately call into the handler that provides semantics. So there's no lookup in that sense. In order to call this operation on a handler, we need to have it available and we need to pass it down. And this is where capability passing style now comes into play. In particular, I want to emphasize that capabilities are an important concept in a Scala Effect. And you can think of a capability in Scala Effect as this trait here, cap E, for some effect signature E. It holds an instance of a handler for that effect signature. Okay. Now I said, yeah, they are very important, but why haven't we seen them yet? And the true story is we have, but it's a tiny bit hidden, and it's hidden in the type signature here, which looks a bit like an extension to Scala, but it's just infix type members, infix type aliases. And one of them is using, and using actually is a function type. It is a function from a capability of effect signature E to something in control A, and the same thing for AND, but it doesn't wrap it into control. And now it's important to note that we have this magic keyword implicit here, which allows us to avoid having to actually pass down these capabilities explicitly, but having the Scala type checker and an implicit inference engine figuring out, okay, this is the capability I need to use here for this effect operation. And we can explicitly desugar this example to see how this actually works. So drunk flip actually is a function of two arguments, the two capabilities, and the effect operations are actually calling into the corresponding capability for the effect signature. And in turn, handlers create capabilities which are then passed down by type. So since the type of the first argument is a capability of AMP, we pass down AMP and XE likewise. I mentioned these three design decisions earlier, and now I want to relate capabilities to these design decisions again. So we had the first decision, which was how do we actually implement how do we get our hands on the continuation, on the context. And capabilities relate to that in that we use them as unique prompt markers in our multi-prompt delimited continuation implementation to delimit the scope of the continuation to be captured. Second, the second question was how do handlers provide semantics? And here we pass down capabilities and they contain the handler implementation. So also here capabilities are related to this design question and to our answer of shallow embeddings. And the third one was how do we establish an effect typing discipline? And here, conceptually, the capability entitles the holder of the capability to trigger an effect operation. So it's a conceptual entity of, or proof that the holder is allowed to call an effect. So now we saw a bit also the design decisions behind effect, and I want to briefly look a tiny bit into extensibility properties which follow from our decisions. Algebraic effects are already very modular and extensible, but since we choose a shallow embedding as the underlying principle behind effect, we also inherit the extensibility properties that shallow embeddings come with. So in the previous talk we have seen object algebras as a structuring principle of the library, and there are also object algebras are very related to shallow embedding. They also inherited the modularity properties from object algebras by that, and the story is very similar here. So if you think of the expression problem, which is, in a nutshell, if you have a program written over some recursive data structure, and you then it's not too easy to add variants to that recursive data type, and at the same time modularly add new functions, new recursive operations over that recursive data type. And we can rephrase that in the setting of effect of algebraic effects when we think of this effect tree as being able to modularly add new effect operations which correspond to variants, and add new handler implementations which correspond to new operations over the effect tree. And indeed, Scala effect enables both ways of modularly adding new either effect operations or handler implementations. So let's look into that. It should be maybe clear from the previous examples that it's not too hard to just write a new handler because it's just implementing a new trait, right? Okay, if adding a handler is implementing a trait, we clearly can do that. Okay, so here we see the XC option handler, which interprets into option, but we clearly can also just write another trait that interprets into either, okay, as an alternative. But we can also add new effect operations, and there are two ways to do that. The first one is we can just add a new effect signature, like we added amp and XC. Also, not a big deal because it's just defining a new trait. But in addition, we can also add new operations to the signature, and this is done by inheritance. So here, the amp choose effect signature inherits from amp and adds one new effect operation. And we can also define handlers now for amp choose, reusing the handler for the amp effect. So we don't need to re-implement flip here. We just add the new case for choose. And this shows that we also support what is often referred to as an independent extensibility. This was coined by Sanger and Nordesky in their paper in 2005. That we can independently add new signatures, new handlers, and by Scala mixing composition we can just throw them together and reuse them. Okay, we don't need to redefine them all the time. And what I think is also quite interesting is that we can handle two effects in one handler, because we just do that by implementing the effect signature, right? So here's an alternative implementation of exceptions, which interprets the program into a list, and it just returns the empty list if there is no result, if there was an exception, and it returns a singleton list if there was no exception. And since we interpret in a list now, we can compose our amp list handler with the exception list handler into one handler, which we call here XC amp list, and use this to handle both effects at the same time. And in fact, this desugars to passing down both and using it in the two positions, once for the capability for exceptions and once for the capability for ambiguity. And this is an example of capability subtyping or handler subtyping. So we also establish a subtyping discipline here. Okay, to conclude, I showed you a library for algebraic effects written in Scala. And one major design decision was that we use a shallow embedding of effect handlers. By doing that, we also inherently implement deep handlers, though nothing prevents us from reifying the tree again and thereby implementing using shallow handlers by that. We've seen that users can define new effects because they can just define a new trait in extending F. I didn't go into detail into that, but we can also have dynamic effect instances. So at runtime, we can create new effects that can be handled. We have seen that a couple of modularity and extensibly scenarios, which are well supported, I think. I didn't also go into detail on that, but we preliminary benchmarks show that we have a good performance improvement over existing libraries which are based on the free monad due to the benefits from the shallow embedding. Finally, we didn't actually manage to achieve safety. The reason for that is that capabilities can actually leak. So I said handlers create new capabilities and they are passed down, all fine, but you can, for instance, store them in a mutable reference cell, and by that they leak outside of the handler scope, and that's not safe. One way to deal with this actually is to mark capabilities as being second class, and using the approach by, for instance, Tjag Rompf and colleagues. And we also experimented with that. So it would be cool to have implicit local functions in Dotty to be used by Scala Effect. And finally, user programs, we also have seen that, are written in monadic style. For Scala developers, that might not be a big deal, but if you want to also have other user groups, I'm particularly thinking of Java users, which perfectly fit, Scala Effect perfectly fits also the Java story, because typing is much easier by using the shallow embedding. So we can also just use Scala Effect in Java. But monadic style might be, with the lambdas maybe not so much, but still a showstopper there. So we're also working on improving that by, we have several different approaches for that. So I'm leaving you with these resources up here. Actually, all the examples can be found under this tiny link, tiny.cc/effect. You're warmly invited to read the paper and contribute on GitHub. Thank you for your attention. Thanks a lot.
So my question is, how far have you gone with respect to trying to make this capability second class, and whether there were any challenges in integrating that with this work?
That's a good question, thanks. So when we try to use this local annotation to make capability second class, I encountered the first barrier I actually encountered is inside of the implementation of Scala Effect, where we do need to store capabilities on the heap. And especially because we, when you program with Scala Effect, you mostly don't program with the JVM stack, but you program with a copy of the stack. And since this is heap allocated, also the capabilities that we use as prompt markers live on the heap somewhere. So they escape the dynamic scope of the handler invocation. So this is a point where we need to escape from the local annotation and mark them as, yes, please trust me, it's okay that I started on a heap. This was a bit of a problem, yes. Good question, thanks. Yes, please.
Can I see the first example, please?
Yes, of course.
Yeah. Here, if you just flip the xc and for using x and so the type of the class, the type of the value changes.
Yes, it changed.
And does the meaning also change, or?
No. So good point. If we look at the desugared variant, right? Sorry, that takes longer than I expected. Capabilities. There. Okay. Good. If you look at the desugared variant, you see this corresponds to these two parameters, right? Since the Scala or the dotty type checking and implicit resolution automatically fills in the capabilities, we can also swap these two arguments. If you explicitly pass them down, because you can always do that, then of course your program will break. But it should not change semantics. It's just the order of the parameters. There's no difference there. What is important is the order of the handlers. And but since the capabilities are passed down by type, you can also flip the parameters of drunk flip here, and the dotty Scala will figure out, okay, no, I also need to flip them in the invocation. Yes. Thanks.
Have you thought or explored potentially using macros to allow users to write in a more direct style?
Yes, that's a good point. There are, as I mentioned, there are many different ways to achieve direct style. One would be to use macros or follow the approach by Ingo Meyer, Tia Kromf on automatically CPS transforming Scala programs. Other options would be to use some bytecode instrumentation, because we only need the monadic style for our implementation of multi-prompt delimited continuations. We could also achieve similar things with bytecode instrumentation. I experimented with that and had achieved good results, but the implementation would be much more fragile because instrumenting bytecode is, it's not that easy that you can just do it in a second. And so we went for a monadic style here. But these are two possible options for that. Yes. Another option would be if the JVM would actually support something like continuations, delimited continuations, fibers, threads, lightweight threads, generators, something like that would help us to implement everything in direct style instead of monadic style.
Yeah.
Cool. Thanks for the question.
All right, thanks everyone. So this concludes the session. Let's thank Jonathan.
Thanks.